Hello everyone, it's Mr. Kennedy here. I hope you're all well and welcome to week 2 of Higher Physics. So we were very impressed with the standard of work that was submitted last week. There were a few issues that came up. Mostly there were issues with rounding numbers in scientific notation and also issues with zero when it comes to significant figures. Sometimes zero is significant and sometimes it isn't, and that can cause a little bit of confusion. So what I'd like to do is I'd like to try and clear that up a little bit. So numbers which are significant are mostly non-zero numbers. The first significant figure is always the first non-zero digit when you're reading from left to right. The second significant figure, however, could be equal to zero. So zeros are significant under either of these two conditions. So if the zero is the last digit after the decimal point, and also if the zero is between the two non-zero numbers. For example, 4,200 has two significant figures, the 4 and the 2. 4,020 has three significant figures, the 4, the 0 and the 2. And 4,020.0 has five significant figures. In this situation, all of them would be significant because the 0 is the first number after the decimal point, so it is also significant. However, care has to be taken here because 4,200, there could be a situation where 4,200 could be given to three significant figures or even four significant figures. However, if this was the case, it would usually be stated clearly with that data. Same with the second example with 4,020. We've said it has three significant figures, but there could be a situation where that could be four significant figures. But again, that would be stated clearly. So we'll say it's three significant figures unless it's stated otherwise. If you need a little bit more information on significant figures, this BBC Bite-size page will give you more information. If you open up the PowerPoint and click on the link, it will take you to that page. So in higher physics, we always need to give our numerical answers to what we call an appropriate number of significant figures. To know what's appropriate, you have to look at the data you've used to calculate your answer. So you should always give your answer to the same number of significant figures as the piece of data you've used that has the smallest number of significant figures. The reason we do this is because of precision. How precise the data is really impacts on how precise our answer can be. We'll learn a bit more about this when we study uncertainties later on in the year. So to help with this is an example. It's a National 5 electricity question. So a motor has a power rating of 12 watts and a voltage of 1.43 volts. What is the value of the current in the motor? So to find the current, we use the formula power equals current times voltage, P equals IV. And then we rearrange for current, which is I equals P over V. We then substitute in the data, so I equals 12 divided by 1.43, and then we get this answer on our calculators. So then we need to make a decision. How many significant figures are we going to give with this answer? So we need to look back to the data we've used. We've used a power rating with two significant figures and a voltage with three significant figures. Therefore, we should give our answer to two significant figures. So our answer should be rounded to 8.4 amps. The SQA do, however, allow a little bit of leeway with this. They will allow you to give up to one too few significant figures or even two too many significant figures. So for this particular question, 8 amps would be an acceptable answer, as would 8.39 amps, as would 8.392 amps. Those would all be acceptable. Okay, so on to this week's work then. This week we're going to be doing really some revision of some key areas from National 5, which are also important for higher, and we'll be building on these over the next few weeks. So we're going to look at speed, velocity, acceleration, and also a bit on vectors and scalars, including displacement. We're going to be carrying out calculations involving all of these, and we're going to look at the resultant of two vectors at right angles to each other. We will look at some more complicated examples next week where things are not at right angles, but for today we're going to stick with examples at right angles to each other. When you're doing all these calculations today, please remember significant figures. Give your answer to an appropriate number of significant figures. So these are the tasks for this week. You're already watching the video clip on speed and acceleration, and we're going to start on that in just a second. You should make notes on these as you go. You might want to pause the video at certain points, or you could also read through the slides yourself. Remember to keep your notes organised in a notebook, a jotter, or even electronically. It's really important because you will need to refer back to these as we progress through the course. Once you've gone through the theory, you should answer the revision questions from pages 1 to 5 of the PDF document, which is attached to Show My Homework. Please show all of your work in. It's much easier to do physics questions by hand than it is electronically, well, the calculation questions anyway. Remember, as I've said already, give an appropriate number of significant figures with your answer. We've also attached the numerical answers to the PDF. It's on pages 6 and 7, so you can check your answers. And then number 4 is really important. Can you please submit photos of your work or electronic versions of your work to your teacher? They will then be able to provide feedback on your work. This is really important so that we can see how you're progressing, maybe give you some help with certain areas, and it also allows us to tailor the next week's work based on what we've seen from the previous week. If you need help, just use the comment function of Show My Homework. You should be spending about an hour on this. So if you feel you don't have enough time or you're running out of time, don't try and do all of the questions. Maybe choose a few questions from each section. You might even do all of the even numbered questions, for example. Okay, so on to the revision. Speed. Speed just means the rate of change of distance, really how much distance something is covering every second or every unit of time. So the units of speed, the standard units of speed are meters per second, which you write as ms to the -1. To calculate speed, we need to know two things. We need the distance travelled and the time taken, and then we use the formula speed equals distance divided by time. Speed, as we've said, is meters per second. Distance tends to be measured in meters, although you can use other units, and time is measured in seconds, although again you can use other units to measure time. So the equation can be shortened to V equals d over t. It's really important that you use V for speed and also for velocity, as we'll see later on in the video why this becomes important. You can use a triangle to help you rearrange. So D would be on the top and V and T would be on the bottom in this particular situation. So to measure average speed, we just need to measure two things. We need to measure a distance. This could be done with a meter stick or a trundle wheel, and a stopwatch would be used to measure time. We then just use the equation, average speed is distance divided by time. If we wanted to do this more precisely, we could use a computer with light gates to find the average speed. So in this situation, as the trolley passes through light gate 1, it will start the electronic timer, and as it passes through light gate 2, it will stop the electronic timer. You will then have the time it takes for the trolley to go between light gate 1 and light gate 2. So if we measure this distance, we can then work out the speed in the same way as before, using distance divided by time. Okay, if we want to measure instantaneous speed, we only use one light gate. We really have to use a light gate to measure instantaneous speed because we're trying to measure the speed over a very short time interval. So in this particular situation, when the mask passes through the light gate, the front edge as it passes through will start the timer, and then when the mask is completely passed through and the beam is complete, the timer will stop. This gives us the time it takes for the mask to pass through the light beam. So we need to know the width of the mask and the time taken to pass through the light beam. The computer will then use the formula speed equals distance divided by time, where the distance this time is the length of the mask and the time in the light gate, and this gives us the instantaneous speed. This can be really useful if you want to find acceleration, because you could find the initial speed and the final speed and measure the time between, and that would allow you to find acceleration. So on to acceleration. If an object's speed is changing, we say that the object is accelerating. If the speed is increasing, we call it a positive acceleration, and if it's decreasing, we call it a negative acceleration or a deceleration. Acceleration is defined as the rate of change of velocity, essentially how quickly the velocity of an object is changing. So an example would be an acceleration of 2 meters per second tells you that the object's velocity is increasing by 2 meters per second. every second. So if it started off at rest at 0 meters per second, after 1 second, its velocity would be 2 meters per second. After 2 seconds, its velocity would be 4 meters per second. After 3 seconds, its velocity would be 6 meters per second, and so on. So to calculate acceleration, we use this formula here. So A is equal to the change in speed, which is written as V minus U, where V is the final speed and U is the initial speed, and that's divided by the time taken. Please be careful that the units of acceleration are meters per second, or meters per second squared, which is written as ms to the minus 2, whereas speed is meters per second, ms to the minus 1. Okay, vectors and scalars. In physics, anything that can be measured is called a quantity or a physical quantity. All physical quantities can be split into one of two groups. Either scalars, these are fully defined by their magnitude, which just means size only. So for example, a time of 3 seconds. Vectors, these are fully defined by their magnitude and a direction. So for example, we might have a force of 5 newtons to the left. So distance is the sum of all the individual distances of a journey, and distance is a scalar quantity. Displacement, however, is a bit different. It's the shortest route between the start and finish points in a straight line, and displacement is a vector quantity. So if I have a look at this example here, if the person started on this point here and they've walked this route to get to the end point, the distance that they've travelled is 3 kilometres. But the displacement is the straight line from start to finish, which is 2.7 kilometres east. We must give a direction with the displacement. There's no need to give a direction with the distance because that is a scalar quantity. Speed is defined as the rate of change of distance. Speed is a scalar quantity, so V equals d over t. And velocity is the rate of change of displacement, which is a vector quantity. And V equals S over T, where S is equal to displacement. So this is, as I was saying at the start of the video, it's really important to use V for speed rather than S, otherwise this becomes quite confusing. Last bit of the video then, to find the resultant of two vectors, the direction of each vector must be taken into account. So for example, if a pupil walks from the Woodmill Physics Department to the Assembly Hall, to do so, they might walk 112 metres north and then 45 metres east. And we'd like to calculate the pupil's final displacement. So I've just written the question again on the left-hand side here, and this is my, my written solutions. So the first thing I've done is I've marked on a start point, and I've also, if you notice here, I've put the direction. So north is towards the top of the page. So the first part of the journey was 112 metres north. So I've drawn that on and just marked an arrow to show the direction. They've then turned and they've walked 45 metres to the east. So again, from the end of that first vector, I've drawn the next vector 45 metres east, and I've just shown an arrow to show the direction. The resultant of those two vectors is then from start to finish in a straight line, and the resultant is indicated with a double arrow. The resultant in this situation is the displacement, or the magnitude of the displacement. So to find the magnitude of the displacement, because this is a right-angled triangle, we can use Pythagoras. So we get the displacement equal to 120 metres, given to two significant figures, because this is to two significant figures. To find the angle, we can use trigonometry. So tan x equals over a, that gives us this angle here is 22 degrees. So our final answer, we can give a displacement of 120 metres at 22 degrees east of north. There are other ways of giving that angle. You could give a bearing of 022, for example, as long as you're clear with your angle. If we then want to find the average speed, if it took 2 minutes for them to travel, the average speed would be the distance divided by the time, which is 1.3 metres per second, and the velocity would be the displacement divided by time, which is 1 metre per second, and we also need to give the direction with the velocity. Okay, so now you're ready to try the questions from the PDF document. Please remember to show all of your work in and to send pictures to your teacher so you can get some feedback. You might be useful to reflect on the success criteria just at the end. And remember, these are the useful physics websites that you should be becoming familiar with. Good luck with this week's tasks. Hope you enjoy them, and just please get in touch if you need any help. Thank you.